Hello, in this video we're going to talk about the spectral theorem. And there are many versions of the spectral theorem, but for us we will talk about the spectral theorem for real symmetric matrices. So these are symmetric matrices with real entries. There are also versions of the spectral theorem for matrices with complex entries, but that's a bit more advanced, and we're just going to stick to matrices with real entries, which is what we've done throughout this series of lectures. And what the theorem says is, the theorem says, so let's say that you have a symmetric matrix. So suppose that A is an n by n symmetric matrix. Then it's possible to find eigenvectors of A that form a basis for Rn. Okay, so the theorem says that then there exist n eigenvectors of A that form, well, if you have n eigenvectors of A, they're not only linearly independent, but they can be chosen to be orthogonal. Then there exist n eigenvectors of A that form an orthonormal basis for Rn. Okay, this is one way to phrase the spectral theorem. And remember what it means for these n vectors to be an orthonormal basis. What it means is, first of all, that they're a basis for Rn. Okay, so the set is linearly independent and spans Rn. And the orthonormal part means that all the vectors, so the eigenvectors, are unit vectors, and that they're orthogonal to each other. Well, if you have eigenvectors, you can always make them unit length just by dividing by the length. So somehow that's not the important part. The important part is that you can choose them to be orthogonal to each other. And we'll take a look at an example. Well, before we get to an example, let's think about what happens if you choose these n eigenvectors that form an orthonormal basis for Rn. So let's call these vectors u1 through un. And let's say you form this matrix Q, which has the ui's as the columns. Well, what kind of matrix is this matrix? If you have, so this is an orthonormal, u1 through un is your orthonormal basis consisting of eigenvectors. These are all eigenvectors of A. What kind of matrix? If you have orthonormal, a set of orthonormal vectors, n orthonormal vectors, and you put them into this matrix, the columns of this matrix Q, what kind of matrix is that? That's an, what's that matrix called? This n by n matrix is an orthogonal matrix. This is an orthogonal matrix. And remember that if you have, so this part, this forming Q part, is the orthonormal basis part. The fact that these vectors are orthonormal means that Q is an orthogonal matrix. An orthonormal basis for Rn means that Q is an orthogonal matrix. Now, what about the part where the ui's are eigenvectors of A? Well, remember that if the ui's are eigenvectors of A, let's say that lambda 1 through lambda n are the corresponding eigenvalues. of the UIs. Then what that means is that if you take the matrix A and you multiply by this matrix Q, okay, so this is the matrix Q, what are you going to get? Well, this is going to be the matrix. Remember, when you have a matrix and you multiply by another matrix on the right, what you're doing is you're multiplying the matrix by each of the columns individually. So this matrix has columns A times U1, A times U2, etc. up to A times UN. Okay. And this is the same as the matrix where you take U1 through UN on the left and then multiply by this diagonal matrix, lambda 1 through lambda n. So again, this is Q, and let's call this matrix lambda. This is the capital lambda, like this. Okay, because remember what you do when you multiply matrices like this, one useful way, so here you're taking this matrix and multiplying each of the columns, and the first column is going to be lambda 1 times U1 plus 0. So remember, if you have a matrix like U1 through UN, and then something like, lambda, and then a bunch of zeros, okay, what this means is that you take linear combinations. When you take a matrix and multiply by a vector, you're taking linear combinations of the columns, right? So this is going to be lambda, this lambda 1, then it's lambda 1 times U1, plus 0 times U2, plus dot dot dot, plus 0 times UN. Okay. So you're just going to get lambda 1 times U1. Okay, that's just a review. And why are these matrices equal? Why is this matrix equal to this matrix? So this matrix is going to be the matrix where the first column is lambda 1 U1, and then the last column is lambda n UN. So why are these two matrices equal? Because A times U1, if lambda 1 through lambda n are the corresponding eigenvalues, then A times U1 is lambda 1 U1, A times U2 is lambda 2 U2, up to A times UN is lambda n UN. So this matrix is the same as this matrix because the columns are the same, right? The A times U1 is equal to lambda 1 U1, A times U2 is, okay, I didn't write it down, but lambda 2 U2 up to A times UN equals lambda n UN. So now we see that A times, so let's write down what we have. We have this matrix A times this matrix Q equals Q times lambda. So A times Q equals Q times lambda. And can we solve for A by itself? What can we do to get from this to get A by itself? We can multiply by Q inverse on the right, right? And Q times Q inverse is the identity matrix, and A times the identity matrix is just A. So you get A times Q lambda Q inverse. And since Q is an orthogonal matrix, this is actually the same as Q lambda Q transpose, because Q transpose is the same as Q inverse because Q is orthogonal. Okay? And so when you have a symmetric matrix, you can express A in this form. So another way to rephrase the spectral theorem is that every matrix, every symmetric matrix A has the form A equals Q times lambda times Q transpose, or Q inverse, where Q is an orthogonal matrix and lambda is a diagonal matrix. Okay. And in this theorem, A might have an eigenvalue of 0, right? These lambda i's might be, some of these might be 0. That's okay. But the ui's are linearly independent. And since the ui's are linearly independent, you have n linearly independent vectors. When you make them the columns of an n by n matrix, that matrix is invertible, right? So Q is definitely invertible. Just in case you're wondering, how do you know that Q is invertible? Because we needed Q to be invertible to be able to do this. All right, let's look at an example. So let's just say that A is this matrix. Okay, let's say that A is the 2 by 2 identity matrix. Well, in this case, every vector is an eigenvector with eigenvalue 1, right? I mean, every matrix V will be equal to A times V if A is the 2 by 2 identity matrix. So an example of an orthonormal basis consisting of eigenvectors of A would be something like U1 is 1, 0, and U2 is 0, 1. That's an example of an orthonormal basis for Rn consisting of eigenvectors of A. Now notice that the theorem doesn't say that whenever you have two eigenvectors, it's an orthonormal basis. I mean, that's certainly not true, right? I mean, if you chose just two random vectors in R2 that are not orthogonal, those will be eigenvectors of A, okay? But they might not be unit length and they might not be orthogonal. So the theorem, just to emphasize, says that it's possible to come up with eigenvectors of A that form an orthonormal basis for Rn. Okay, so let's look at another example. Let's say that A is this matrix, 2, 0, 0, 3. Well, again, you can also choose U1 to be 1, 0. That's an eigenvector with eigenvalue 2, and U2 to be 0, 1. That's an eigenvector with eigenvalue 3. These two vectors, U1 and U2, are orthogonal, and they have unit length. What if you had something like A equals, let's do another diagonal matrix. 2, 0, 0, 0, 3, 0, 0, 0, 3. Well, then you can pick U1 to be 1, 0, 0. What about U2 and U3? They can be 0, 1, 0, and U3 is 0, 0, 1. Right. Now here you actually have lots of options for U2 and U3, because what's going on is this matrix is going to stretch the x-axis by a factor of 2, and it's gonna stretch the yz plane by a factor of 3. So your U2 and U3 can just be any two perpendicular unit vectors on the yz plane. All right, let's do a more complicated example where you actually have to do a lot more computations. So let's say that A is this matrix. And I'm going to use this matrix in in a future video, so I want to do the computation out here. So this is a symmetric matrix, right? Because when you take the transpose, you get itself. But how can we write A in the form Q lambda Q inverse, where Q is orthogonal and lambda is diagonal? Well, if you look at the theorem, we actually saw where the Q and the lambda came from. They came from this matrix lambda was a diagonal entry where the lambda i's were the eigenvalues of the corresponding ui's, and the ui's were the eigenvectors. And so what we need to do is we need to find the eigenvalues and eigenvectors of this matrix A. So let's do it. So the first step is to find the eigenvalues. Right? So to do that, we need the characteristic polynomial. And for a 2 by 2 matrix, remember that it's easy to find the characteristic polynomial. It's P of lambda equals lambda squared minus the trace. That's the sum of the diagonal entries. That's 3. So it's minus 3 and then times lambda plus the determinant. Okay, so just recall that for 2 by 2 matrices, it's P of lambda is lambda squared minus the trace of A times lambda plus the determinant of A. That's a useful fact because it makes it easier to find the characteristic polynomial. Okay, so now we need to add the determinant. That's 1 times 2 minus root 6 times root 6. So that's 2 minus 6, that's negative 4. Okay. And we need to set this equal to 0 and solve. So we can factor this as what? Lambda minus 4 times lambda plus 1. So then we get lambda is equal to 4 and lambda is negative 1. So now we need to find so those are the eigenvalues. And now let's find the corresponding eigenvectors. So let's call the first one lambda 1, the second one lambda 2. Okay, so for lambda 1, which is 4, we want to do A minus lambda I, so that's A minus 4I, and then that's going to be, okay, where's my A? So you just subtract 4 on the diagonal, so you get negative 3, root 6, negative 2. And remember, what's special about this matrix? If you have a eigenvalue lambda and you do A minus lambda I, that matrix is not, it's not invertible, right? The determinant of this matrix is 0. So when you row reduce, you're going to get a 0 row. So you're going to get this. And now we need to solve A minus 4I, this matrix, times x equals 0, 0. Right? And then since we row reduced, we can just solve this matrix times x equals 0. And we just need to find a vector that's orthogonal to this matrix, to this first vector. And do you know the trick to find a vector that's orthogonal to a vector in R2? If you have some vector like AB, if you take the dot product of B negative A, then you're just going to get 0, right? So you can just swap the order and then put a negative sign. Or if you do AB dot negative BA, you're also going to get 0. So you just switch the order and then stick a negative sign somewhere, and that's going to give you a vector that's orthogonal to that vector. And so we can pick, so one unit vector would be x1, which is, okay, root 6 and then 3. And this is an eigenvector of A with eigenvalue 4, but it's not a unit length vector. So what we should do, that's why I called it x1 instead of u1. So we should find the length of this. So the length of this vector is going to be, what is it? So this implies that the magnitude of x1 is the square root of square root of 6 squared is 6 plus 3 squared is 9, so it's the square root of 15. Okay? And now we can normalize this eigenvector by dividing by the square root of 15. Now you could do some algebra. Am I going to do the algebra? Yeah, I guess I will do the algebra. So I'll write this as root 6 over root 15, 3 over root 15, and now we need to, I guess it's a little better to simplify this. So let's see. So the first one is root 6 over root 15. That's root 6 over 15, and then that's root 2 over 3. No, 2 over 5. So it's the square root of 2 over 5, which you can write as, if you multiply both sides by root 5, multiply top and bottom, you're going to get root 10 over 5, right? So the square root of 10 over 5. And then 3 over the square root of 15, I can write this as, I can multiply both sides by the square root of 15, and then this is 3 times the square root of 15 over 15. And then I can write the bottom as 5. So it's the square root of 15 over 5. Okay. Maybe not the... It might actually be easier to leave it the first way, but anyway, I already did it. So that's u1. That's an eigenvector with unit length with eigenvalue 4. Now we just need to do the other one. So it's lambda 2, which is, what was it, negative 1. So now we need to do a minus lambda I. So that's a plus I, and that's going to be 2 root 6, 3. And again, this when you row reduce, you're going to get a 0 row here. And so you just need to find a vector that's orthogonal to 2 root 6. And so we just do the same thing again, where you swap the order and then stick a negative sign. So you can pick x2 to be root 6 and then negative 2. All right, and so once you do this, we again need to find the length. So the length of this vector is the square root of the first component squared, that's 6, plus the second component squared is 4, so you get root 10. Okay, I think this time, instead of messing around with the algebra, I'm just going to leave it as root 6 over root 10, negative 2 over root 10. Okay. So that's unit length eigenvector with eigenvalue negative 1. And now we're ready to figure out, well, now we can say what Q is, right? We can just form Q to be the matrix where you have columns U1 and U2. So here's my U1, and there's my U2. And if I just make it so I can see both of them, then I get Q where the first column is root 10 over 5, root 15 over 5. Second column is root 6 over root 10, negative 2 over root 10. So that's my Q. And my lambda is the matrix with eigenvalues, with diagonal entries being the eigenvalues. So that's 4 and negative 1. And remember, I need to make sure that my Q and lambda are compatible. So I need to make sure that this first column is an eigenvector with the first eigenvalue, and that this column is actually an eigenvector with this eigenvalue. Right? And typically when you write lambda, you can swap the order and put the negative 1 first and then the 4 instead of the other way around, but typically you can make the first row the biggest, like the most positive number, so from greatest to least when you write from left to right. Okay, that's a convention. And so we see that A is equal to Q and again, you can simplify, you can get rid of the radical sign on the bottom if you really want, but I'll just leave it there. So it's that times lambda times Q inverse. Well, remember, for a 2x2 matrix, okay, there's a formula for the inverse, but for an orthogonal matrix, it's even easier, right? How do you find the inverse? What's the fast way to find the inverse of an orthogonal matrix? You just write the transpose, because for an orthogonal matrix, the inverse is the same as the transpose. So let's just take the transpose of that matrix, Q, and so we get, we get this. And that's our matrix factorization of the symmetric matrix A. Okay? And in a future, well, it's a video that I already made, but in a different video, I did an example of a 3x3 matrix. All right, that's a long enough video. So let's just review what we did. We stated, we didn't prove, but we stated the spectral theorem for real symmetric matrices, which says that every symmetric matrix, there's a basis for Rn consisting of orthonormal eigenvectors of A. And the matrix, kind of, one way to think about it in terms of matrix factorization is that whenever you have a symmetric matrix, it has this form Q lambda Q inverse, or Q lambda Q transpose, where Q is orthogonal and lambda is a diagonal matrix. And we saw, some easy examples where you have a diagonal matrix. I mean, that's simple. And then for a more complicated example, we found the eigenvalues and eigenvectors. And Q consists of unit length eigenvectors, and lambda consists of the eigenvalues. And we did all the computations to do a example by hand. All right, thanks for watching.